Hi, welcome to this short video on the solution for the fourth probabilistic programming assignment. So now your task is to specify a model that we'll be using to estimate both states and process noise precision simultaneously in a linear Gaussian dynamical system. So what you can see here is my source notebook. This is where I make all of the assignments, and then you're given a release version of that notebook where certain parts have been hidden. So if we scroll down to the assignment, what you see here, this is the signal that's been given to you, and these are the equations that govern that signal. So at every point in time, the state is based on the previous state plus some Gaussian noise on top of that, and then the observation is generated by the current state plus another Gaussian noise term. And these noise terms, W and V, are draws from Gaussian distributions, as I mentioned. And so the convention with this n thing, you've seen this before throughout the course, the convention with this n thing is that we describe the second thing as the variance. So tau inverse is the variance parameter of this Gaussian. Which means that considering the precision is the inverse of variance, so what we're saying is that tau is the precision parameter in this noise noise variable, as is gamma for this v noise variable. So the assignment is that you should add a variable tau and the variable xk to the model specification that is partially given below. I've given you the hint that the prior for tau should contain two placeholders, placeholder tau 1 and tau 2. So forgive me, this misses, well, the tau 1 is not complete here, it just says 1. This has been addressed in Piazza already. So what are these placeholders and why should you use them? So as I mentioned in the session on dynamic models in probabilistic programming, what we do is we define a subgraph and we apply that for every point in time. This is sort of a small model that we slide over the signal as time evolves. And so when we estimate a state, the parameters of that estimate, those are the posterior parameters for that state estimate, they become the parameters of the state prior at the next time step. And so that's how you can evolve this belief for states. So this is what we do for priors, and then so because gamma is a precision parameter, it's a time invariant parameter, it's not a time varying parameter, it doesn't change every time step, but our beliefs about this time invariant parameter do change over time, because we start out with some prior, then we make an observation, and then we update our belief for the precision, and then we make another observation, and then we update our belief for the precision again. So the estimates might change over time, even though we think that the underlying parameter is in fact time invariant. And so to facilitate this process of updating your belief for this precision parameter, we maintain these placeholders. And so what is happening at any point in time, we have some prior for the gamma. So you could start with, for instance, 1,1, and then you make an observation, and then you combine the prior with the likelihood to produce a posterior estimate for tau, and then you want that gives you two new parameters. So this a and b for gamma distribution, they're no longer 1,1, they're different values. And then you move forward in time, and then you would like to pass these new a and b's as the parameters for your prior for tau, because then once again those parameters come in, and then a new observation is made, and information from that observation is combined with your previous belief, your prior belief, to form another posterior belief, and then as you again move forward in time, those are again combined. So this placeholder construction is a way to recursively update your belief for this process noise precision. Then the state transition, so this is fairly straightforward because this matches the probabilistic programming session exactly, actually, and it also matches this equation. So the current state is centered on the previous state xk minus 1, and then well, so here you can see it, Gaussian white noise is added to it, but if you would integrate out WK, then you would be left with xk follows a Gaussian distribution centered at xk minus 1 with precision tau, or with variance tau inverse, but that's the same as saying with precision tau. So that's what we see here, Gaussian mean precision with centered at xk minus 1 with precision parameter tau. So that's it. That produces the following graph. Excuse me. And then here are the tests to check whether your model specification was complete. And then these are your inference results. So the states should they should adhere, or the inferred state should adhere somewhat to the observations, and then your inferred precision should rise over time. So your belief for the precision is that, initially you were unsure about these states, you would think that there's a lot of measurement noise, but as you make more and more observations, you're starting to believe that the observations are actually quite precise, or at least of this value of precision. Yep, that's it. If you have any further questions about this assignment, just post them in Piazza. I hope it's been fun. I hope you've learned a lot from these probabilistic programming sessions. I hope you've learned a lot from the entire course. We've had a lot of fun making it, and I hope sincerely that this will be useful for you in the future. Yeah, so the only thing left to say is best of luck with studying for the exam.